All right, so today we're going to learn how to sketch polynomial graphs. So when I say sketch, I mean we're not going to make a big table and calculate like 10 points. That would take a long time. We're going to learn how to quickly sketch the general shape of the graph. Okay, so in order to do that, we need to find some patterns. Okay, so the section down here, you see for each equation, I've done the graph for you. Okay, so some of these can be factored. So like this equation, this is the factored form, and then here's the actual graph of it. Okay, so the graph is below the equations. Make sure you don't get confused. Okay, so the first thing I want us to do is to just focus on the end behavior. Okay, so end behavior means what happens as you go forever to the right, meaning as x goes towards positive infinity, and also what happens as you go forever to the left, meaning as x goes to negative infinity. Okay, so this top left graph, the graph of y equals x minus 1, you can see that as the graph continues to the right, the y values are going upward forever. So we say that as x approaches infinity, as you go forever to the right, the y values are going upward forever. So the y values are approaching positive infinity. Okay, and then you do the same thing as x approaches negative infinity, right? You see that the negative x values go left. So as the graph continues left, you can see the y values are going downward towards negative infinity. Okay, I'll do this one too. So this is the graph of y equals negative x minus 1. Okay, so as x approaches infinity, as it goes forever to the right, you can see the y values are going downward. Okay, so y is approaching negative infinity. On the other end, as x approaches negative infinity, as the graph goes to the left, the y values are now going upward towards positive infinity. Okay, so that's what I'll ask you to do for the rest of these graphs. So go and take a couple of minutes to do that, please. Okay, so now let's try to group together the ones with the same end behavior. Okay, so let's see all the graphs that have the end behavior that's the same as the first one. Okay, so I'll shade it in for us, so I'll color code it. Okay, so I'm gonna highlight all the graphs that as x goes to the right, y goes up. As x goes to the left, y goes down. Okay, so which other ones have that same end behavior? The one right below it. And the one below that. Okay, so this left column all has the same end behavior, right? And you can see from the graph, they all have the same general shape, right? They all point to the top right, and they also point to the bottom left. Okay, so the fact that they share the same end behavior means that they should have something in common in terms of the equation. Okay, so similarly, the next column, these all point to the top left and bottom right. Okay, so it's all by columns, so you don't need to highlight, but all right, so those three have something in common. These three, and then these three. Okay, so again, each column, the end behavior is the same. So I'd like you to look at the left column first and see, okay, what do all the equations have in common? Okay, and that should be different than the second column, right? Something should be different, which causes the end behaviors to be different. Okay, so I'd like you to take a minute and again, look through each column and see if you can find, oh, all the equations in this column have this property or properties. Okay, and then do the same thing for the rest of the columns. Okay, so I'll give you guys some time to look through. X minus 1. Okay, so I see. Sometimes it's a in the factored form, right? Yeah, that's true. There's an x minus 1 in every equation. Yes, David? Okay, so Dalen said two things. Let's go through them one by one. So first he said they're all positive. Okay, so if you look at the first term, x cubed, x to the fifth, they're all positive. There's no negative sign in front of them, so that's definitely true. And Dalen also said odd degree. Okay, so this is degree 1, invisible 1. For this one, the highest degree is the first one of 3. And then over here, the highest degree is 5. So yes, 1, 3, and 5 are all odd numbers. Okay, so I'll just say up here, so odd degree and positive for this column. Okay, so it seems like all odd degree polynomials that are positive point to the bottom left corner and the top right corner. Okay, so let's see if we can do a similar pattern for the next column. All right, so these all point to the top left and bottom right corners. Okay, so these are all negative. These all have a negative in front, but they are still odd degrees, 1, 3, and 5 again. Okay, so the second column is negative, or let's do, sorry, I'll say this first. It's still odd degree, but negative. Okay, so how about the third column? These all point to the top left and top right corners. So both ends go upward. Okay, so this time the degrees are 2, 4, and 6. So these are all even degrees, and the sign in front is all positive. Okay, and then lastly, over here, these all point to the bottom left and bottom right corners, so both ends are negative. Okay, and we can see that they all have an even degree, and they all have a negative in front. Okay, and just to be clear, when we say negative, we're only talking about the leading coefficient, the number in front, the biggest term, right? So we ignore the plus 4. We're looking for whether that highest exponent is positive or negative. Okay, so great. We were able to see that the end behavior can be determined by two things, whether the degree is odd or even, and whether that highest exponent term is positive or negative. Okay, so going forward, we should be able to very quickly determine the end behavior of any function. Okay, so down here, we're going to make a little chart to represent this. It's a little 2x2 box. So again, as Dalen said, one thing we need to consider is whether it's odd degree or even degree. And the other factor is whether that highest exponent term is positive or negative. Okay, so just copying the info from over here. Odd degree and positive, those point to the bottom left and bottom right corners. Okay, so again, it may have some wiggles in the middle, but the end behavior is bottom left and top right. Okay, so on here, I'm just gonna draw the end behavior, bottom left and top right. Again, it may have some wiggles in the middle, but the end behavior is what we're focusing on right now. Okay, so next, odd degree and negative. That's the second column. So that's top left and bottom right. Okay, the third column, even degree positive. Both ends are upward, top left and top right. And lastly, even degree and negative. That's the last column. So both ends are pointing downward. Okay, so this chart will be very helpful to us. So please make sure you have it down. We'll be referencing it throughout today. Okay, and then in addition to the end behavior, we also want to understand the relationship of the equation to the y-intercept. Okay, so the y-intercept is where the graph crosses the y-axis. Okay, so here the y-intercept is -1. Right here, the y-intercept is also -1. Here, the y-intercept is +1. Here, the y-intercept is 0. Okay, and so on. Okay, so I'm asking you to find a connection between the equation and the y-intercept. Okay, so again, go ahead and take a minute to look through and see if you can find the easy way, I guess, to find the y-intercept from the equation. Okay, so did anyone find the pattern or the connection between the equation and the y-intercept on the graph? Yes, please. Okay, so I think you mean the right thing, but coefficients. Okay, the last number without an x in it. Good. So does anyone know what word we're looking for? The term without an x? Constant, yeah. Okay, so yeah, the constant, the term without dx, is the y-intercept, right? -1, -1, -1, -1, +1, +1. And here you can consider the constant to be an invisible +0 at the end. So y-intercept is 0. Okay, so where in the function equation do you see the y-intercept? The constant, which again is the term with no x. Okay, and one last thing we need in order to sketch graphs is what we call the behavior at each root. Okay, so first of all, remember roots are basically x-intercepts. They're the x values where y equals 0. So that means where it touches the x-axis. Okay, so sometimes the graph kind of goes straight through the root, like in virtually a straight line. Okay, so like if we look up here, at this root, at this x-intercept, the graph is a straight line. It goes straight through. Okay, same thing over here, straight through. Down here, straight through. All right, so again, sometimes the graph goes in a straight line through the point. Okay, but sometimes it instead bounces off the x-axis. Okay, so like if we look over here, right here, the graph doesn't go through the x-axis, it bounces off. Okay, so over here also, it bounces off, right, bounces off. Okay, and then lastly, sometimes it curves through. Okay, so it doesn't go straight through, right? It's not a straight line, but it curves through the graph. Okay, so we need to understand, right, for each of these roots, for each of these times the graph touches the x-axis, how do we know if it goes straight through, bounces off, or curves through? Okay, so again, it has to do with the equation. Okay, and I'll give you guys a hint. Everything so far has been based off the what we call standard form, the equation with no parentheses. But I also gave you the factored form. Right, so the factored form is how we're going to find the behavior at each root. Okay. So for example, if we look at this one over here, this is the second row on the right. Okay, given the factored form, we can find the roots. Remember, the roots are where you set each part equal to 0. Hi. So I actually already sent them over. Thank you. Yeah.
Thank you.
Okay, so then to get rid of the exponent of 3, we are going to cube root both sides of the equation. Okay, so we see that we have one root of x equals 0. And then over here, we have another root of x equals 2. Okay, but we can also see that the graph acts differently at these two roots, right? At the root of x equals 0, the graph curves through, while at the root of x equals 2, the graph goes straight through. Okay, so let's look at we'll go to this one. Okay, so here we have x minus 2 in parentheses squared. So again, to find the root, you would just set it equal to 0. First, you need to undo the exponent of 2, so you can square root both sides. And then to undo the minus 2, you add 2. Okay, so we see that x equals 2 is a root that matches the graph. Okay, but this time the graph bounces off the root. It doesn't cross through to the other side. It doesn't go from above to below. It starts above and it stays above. Okay, so looking at those together, those graphs, right, we see that, okay, there's exponents of various amounts, right? So over here where the exponent was 2, the graph bounced off. Okay, and if you look at the other ones, it's the same thing. Okay, so like right here, right? All of these are exponents of 2. And you see for the graph, every single time it just bounces off. It never crosses through. Okay, on the other hand, the exponent of 3, which led to the root of 0, this is where it curves through. Okay, so you can see that over here also. The root of -1, it just curves through. Okay, and then lastly, the root with an exponent of invisible 1, here it just crosses through. Okay, so let's write that last pattern. Okay, so when does the function pass through the root, meaning one of these two situations? We say so this is a new vocab term for most of us. Okay, so we say that the root has multiplicity 1. Okay, and how do you know the multiplicity? You look at the exponent of the factor. Okay, and then, so it's going to be similar for the next two. So the graph bounces off the root when the multiplicity is 2. Okay, and then lastly, it curves through when it's multiplicity 3. Okay, so the patterns we learned on this front page are going to allow us to very quickly sketch a graph. Okay, so again, let's quickly remember the patterns, but we'll be flipping back to this first page throughout today. Okay, so again, based on the positive or negative first term, and then whether it's even or odd degree, that tells us the end behavior. The y-intercept comes from the constant. And then at each root, we know whether the graph will cross through, bounce off, or curve through based on the multiplicity. Okay, so let's go ahead and see how we can put it all together. Okay, so let's turn to the second page. Okay, so here we're given x cubed times x minus 2 squared times x plus 1. Okay, so this is currently in what we call factored form, right? It's all things multiplied together. Any plus or minus signs are within parentheses. Okay, so factored form is actually very useful, as we saw on the previous page, but let's just quickly practice how do you convert it to polynomial form. Okay, so there's several things to do, but for now, I'm going to keep the x cubed the same. I'm going to keep the x plus 1 the same. And I'm just going to focus on simplifying the x minus 2 squared right now. Okay, so this exponent is outside of the parentheses, so that means that it affects the whole thing, so you need to write the parentheses twice. Okay, and then now you distribute. X times x is x squared. X times negative 2 is minus 2x. Negative 2 times x is another minus 2x. Negative 2 times negative 2 is plus 4. So combining those like terms in the middle, we get x squared minus 4x plus 4. Okay, so again, that replaces the x minus 2 squared. Okay, so next you can either multiply these together first or these together first. It doesn't really matter. Yeah, but when you have three things to multiply, you just multiply two of them together, then take that answer times the third. Okay, so I'm going to keep the third one the same for now, and I'll focus on multiplying the first two parts together. Okay, so again, we do need to distribute. X cubed times x squared is x to the fifth. X cubed times negative 4x is minus 4x to the fourth. X cubed times positive 4 is plus 4x cubed. Okay, and then lastly, we need to multiply these together. Okay, so again, there's different ways to do it. As you guys saw in Delta Math, you can make like a rectangle box. You can do a 2x3 box because it's 2 terms here, 3 terms here. I prefer to do it, well, okay, I'll just do it that way because that's the way that you guys are probably most used to seeing it. Okay, so here I've got the x plus 1. And then down the other direction, I'll put the trinomial, the thing with 3 terms. Okay, and it works a lot better if you put the exponents in order from biggest to smallest. Okay, so for each inner box, you just multiply together the row and column it's in. So x to the fifth times x is x to the sixth. X to the fifth times positive 1 is plus x to the fifth. Negative 4x to the fourth times x would be negative 4x to the fifth. Negative 4x to the fourth times positive 1. Negative times positive is negative. Positive 4x cubed times x is positive 4x to the fourth. Positive 4x cubed times 1 is positive 4x cubed. Okay, so now we can combine any like terms. Okay, so the x to the 6 has no other x to the 6 to combine with, so it goes straight to the answer. Then we have negative 4x to the 5th plus invisible 1x to the 5th. So negative 4 plus invisible 1 would be negative 3. Next, we have positive 4x to the 4th minus 4x to the 4th. So those cancel out to 0. They go away. And then you have a leftover plus 4x cubed with nothing to combine with. Okay, so that's how you convert to polynomial form. So no parentheses. Okay, so now we're ready to apply the patterns from the previous page. Okay, so end behavior. So the determining factors for the end behavior, the highest degree is 6, which is even. And then the leading term, the term with the biggest exponent, it's positive, right? It's invisible positive 1. Okay, so let's flip back to the chart on the front page to remind ourselves what's the end behavior when the polynomial has an even degree and is positive. Okay, even degree and positive means both ends point upward. So both ends go towards positive infinity. Okay, so that's the way to state the end behavior, but I always like to just draw a little picture. Okay, so both ends are going to point upward. Okay, next to the y-intercept. Okay, so remember Flint helped us with this one. The y-intercept is the constant of the polynomial. Okay, so here we don't see any terms without x's. So the constant would be an invisible plus 0 at the end. Okay, so the y-intercept is 0. The graph will cross the y-axis at 0. Okay, now for part D, roots with multiplicity. Okay, so sorry, I actually changed my mind about how we're going to do this after I already printed. So we're going to skip part E so you can write in that space if you need. Okay, but the roots with multiplicity, we don't want the polynomial form. We want to go back to the factored form. Okay, so wherever you have room, right, each of these 3 parts has a root. Okay, so that first one, x cubed, where does that equal 0? Okay, so the cubed part can go away by cube rooting both sides. Okay, so x equals 0 is a root, but because of that initial exponent, we say that this root has multiplicity 3. Okay, so I just say MULT to represent the long word multiplicity. Okay, so one of the roots is x equals 0, and that one has multiplicity 3. Okay, so same thing with the next part. You set the next root equal to 0. Okay, so now a little shortcut. You don't really need to put the squared because you're just going to square root 0 and it's going to go away. Okay, so you just take the inside part. You set x minus 2 equal to 0. Okay, so another root is x equals positive 2. But now is where the exponent matters. Because the exponent was 2, we say that this root has multiplicity 2. And lastly, set the last part equal to 0 and solve for x. Okay, so here we have a root of x equals negative 1. And the exponent is invisible 1, so multiplicity 1. Okay, so we're going to take this information and put it all together on the graph below. Okay, so again, we're going to skip party. Okay, so sketch showing all relevant features. Okay, so the first thing we figured out is the end behavior. The graph is going to point to the top left and top right corners. Okay, so all I want you to do on this graph is put a little dot in the top left and the top right. Okay, we're going to figure out what happens in between, but just from the end behavior, we know the graph will start in the top left and then it'll end in the top right. Okay, the next thing we did was we found the y-intercept. So the y-intercept of 0 means the graph crosses the y-axis at 0. So I'll go ahead and put a point at the y value of 0. Okay, in case you can't see it, it's right here. Okay, next, the roots with multiplicity. So I wrote it up at the top, but let me just copy it right here real fast. So we had x equals 0 with a multiplicity of 3. We had x equals 2 with a multiplicity of 2. And then we had x equals -1 with a multiplicity of 1. Okay, so first of all, a root means that it's an x-intercept. So we will put an x-intercept at x equals 0, which overlaps the y-intercept. The origin is both an x and a y-intercept. We also have a root at x equals 2. Okay, so I'm just going to jump to this point and mark it as 2. You don't need to put the tick mark in between if you don't want. Okay, and we also have a root at x equals -1. Okay, so sorry, those should all be points. Okay, so we have the end behavior, we have the y-intercept, and we have the roots. So now we need to know how to connect up the points, basically. So this is where the multiplicity comes in. Okay, so I'll just go in order. So the root of x equals 0 has multiplicity 3. And we saw the pattern on the previous page. Multiplicity 3 means that the root curves through. Okay, so I'm going to say right here, at the root of 0, it's going to curve through. Okay, once we understand, you don't need to write these words anymore, but just these first maybe 2 times will do it. Okay, the multiplicity 2 root means it bounces off. Okay, so the root of x equals 2, multiplicity 2, the graph will bounce off. Okay, and then lastly, the root of x equals -1 has multiplicity 1, which means that it passes through. Okay, so this is all the information we need to sketch the graph. Okay, so now we're basically just going to play connect the dots from left to right. Okay, so start at the end behavior on the left. So start at the top. Okay, and then head towards the leftmost root, the leftmost x-intercept, but stop a little bit short. Okay, so at each root, you need to determine what are you going to do? Are you going to pass through, bounce off, or curve through? Okay, we can see that from the multiplicity at this root of x equals -1, the graph just passes through. Okay, so just draw your line straight through. Okay, and then curve towards the next root, but again, stop a little bit short. Okay, so what do you do at this next root? From the multiplicity of 3, we know that you are going to curve through the root. Okay, so you do go through it, but you kind of flatten out in the middle. All right, so that's what it looks like to curve through. Okay, head towards the last root of x equals 2. From the multiplicity of 2, we know that the graph is going to bounce off. Okay, so bounce off means you don't cross through, you stay on the same side. There's no more roots, so you head to the end behavior and you're done. Okay, and you just draw arrows on both ends. Okay, so I'm gonna do that one more time just to let you guys follow along. Okay, so you always start on the left end behavior, head towards the first root. Because this root had multiplicity 1, I know that the graph will pass through it, so I just go straight through. Head towards the next root. The root of x equals 0 had multiplicity 3, so it's going to curve through. It's going to kind of flatten out in the middle, but then still go through. Head towards the last root. The root of x equals 2 has multiplicity 2, so it's going to bounce off. And once there's no more roots, you just head to the end behavior. If you're on the wrong side of the graph, if you were at the bottom, then you would know you made a mistake because the end behavior has to be at the top. Okay, so this is an accurate sketch of the polynomial. It's got the correct end behavior, it's got the correct y-intercept, it has the correct x-intercepts, and it is correctly interacting with each of the roots. Okay, so we'll start the next one together, but then I'll give you some opportunities to practice. Okay, so this next one, x times x plus 3 times x minus 1 quantity cubed. Okay, so just to save us time, please copy down. This is the polynomial form if you were to multiply it all out. Okay, so from that, go ahead and try to find the end behavior, please. Right, so look at the polynomial, use the chart on the front page, and fill out the end behavior. Okay, so I will be randomly calling on someone for this part. So if you're not sure, turn to someone nearby and ask them what they did. Okay, you guys have had the chance to ask for help if needed. So just a reminder, if they get it wrong, that's part of the learning process. Thank you. Okay, so what do we do to find the end behavior? Let me ask. You're not here. Lily, were you able to find this? Okay, you're correct. Can you explain how you came up with that? All right, thank you. Can anyone help us out? Yes, thank you, Winston. Perfect. Okay, the biggest exponent, so the degree of 5 is odd, and that term is positive. So positive and odd is top right and bottom left. Okay, so why don't we do the graph as we go? Okay, so as you go to the right, the y value is going upward. So we're going to end in the top right. But as you go to the left, the graph is going downward. So this one's going to start in the bottom left, not the top left. Okay, so go ahead and put those two little dots in the corners so that we know where we're going to start and where we're going to end. Okay, y-intercept. So here we look for the constant. So constant, there's no term at the end without an x, so it's an invisible plus 0 again. Okay, so that means the y-intercept would be at the origin. Okay, roots with multiplicity. So here we're going to want to go back to the factored form. Okay, this outer x, you just set it equal to 0. And this has multiplicity of invisible 1. Okay, so multiplicity is 1. The next factor of x plus 3, where does that equal 0? At x equals -3. Okay, so that root also has multiplicity of 1 because the exponent is invisible 1. Okay, and the last one, the factor of x minus 1, that leads to a root of x equals +1. And this one does have an exponent of 3. So the multiplicity of this root is 3. Okay, so the 3 roots, x equals 0, multiplicity 1, x equals -3, multiplicity 1, and x equals 1, multiplicity 3. Okay, again, we're going to skip letter E for this whole packet. Okay, so let's go ahead and mark those 3 roots on our graph. Okay, so x equals 0, multiplicity 1, that overlaps with the y-intercept. Okay, and then we also have an x-intercept or a root at x equals -3. That one will also have multiplicity 1. Okay, and then x equals 1 has multiplicity 3. Okay, so again, for now, I'll write in words the action at each root, but once you get comfortable, you won't need to write it in. Okay, so going from left to right, the root of x equals -3 has multiplicity 1. Okay, so I'm just going to say multiplicity 1. Okay, so multiplicity 1 means it passes through. Okay, the next root, x equals 0, also multiplicity 1. So that will also pass through. But lastly, the root of x equals 1 has multiplicity 3. So that one will curve through. Okay, so now I would like you to try this part. Okay, so you need to connect the dots from left to right, but remember, you need to follow the instructions at each of the roots. Okay, so go ahead and try it out, and let me know if you have any questions.